here's some interesting history based on the idea of empty space argument. And Albert Einstein, toward the end of his life, as we all know, had a lot of misgivings about some of his earlier ideas, and here's an expression of one of them. I consider it quite possible now that physics cannot be the basis of the field concept, and I have to be clear here, his meaning of the field concept may be different than other people's meaning, but he meant particularly the general relativity field idea, that space bends and all these kinds of things. Okay, in other words, and he's thinking of continuous structures. I don't want to get into that. The main meat of this quote is, in that case, there remains nothing of my entire castle in the air, gravitational theory included, and the rest of modern physics. Modern physics, which is basically all based on the idea of empty space, ultimately. The idea that everything is, all the energy of the particle, everything about the particle is localized where the particle is. It's not extensive through space. That's really the bottom line. And that's what Einstein is coming to grips with, could never really resolve. And he's recognizing that. And here's Feynman's famous quote. I think you've probably all heard this before. What I'm going to tell you is that we teach our physics students in the 3rd or 4th year of graduate school. It's like, I think of this as sort of a mystery thing. You don't get to hear this until later on. I'm telling you now the secret. It's my task to convince you not to turn away from quantum electrodynamics just because you don't understand it. My physics students don't understand it either, because I don't understand it either. Nobody does. And it's true. And he was proud of it. I don't know. But, okay. At this point, the chapter switches gears, and we're going back into a little more history. So we've established now, really, the importance of the idea of a non-empty space, and what consequences that has had. Now we're going to go back and develop the ideas behind Rado's theory. And we have to go back a few centuries to do that. No, please. Not yet. Okay, we have 3 players in the early days, and this is listed more or less in chronological order. Three players that had some very profound influence on our thinking about dynamics early on. Kepler, of course, because he just was an empiricist. He noticed these empirical laws that follow mathematical relationships, and he said it's a mysterious harmony. It has really no idea whatsoever of the mechanism. He's just recognizing the quantitative relationships. And then comes Descartes, and he says, well, you know, there's this solar vortex idea, this idea of the sun being the center of something, because this is, again, Copernican ideas are new. He's coming with the idea of a vortex theory, and actually has some very interesting ideas related to vortex. The problem, as Rado points out, is that his mathematics were faulty. And that's really a shame, because his ideas weren't all that bad. And when you have good ideas and bad mathematics, it can do more harm than good. And that's actually what happened. It's just a historical fact. Newton came along, of course, and he defined some new ideas, a whole new way, really, of thinking of things. The concept of force was new. The concept of mass was new. Can you imagine a physics without the concept of mass? I mean, really, that's what they had in the days before Newton. So all of these ideas were new. Really, interestingly, never thought, not F, not M, not A. They were all new. So, okay, let's go on. New solution, which Rado is critical of, is that is F equals ma. And the point he wants to make, he's thinking in terms of the Galileo famous rock experiment. You got a heavy rock and a small rock, and they both fall at the same rate. Okay, ignoring air resistance and things like that. And in Newton's case, what we've done is complicated the whole mix by having a force. In other words, the force acting on the larger object is greater, but the mass of the object is also greater in great proportion, so that the ratio, the F over m, is constant. And Rado is critical of that, because why have them at all if we're just going to cancel them out? We got this one arbitrary thing, and we divide it by some other arbitrary thing. We always get the same answer, which is the gravitational potential. Why not just have the gravitational potential? Am I saying this correctly?
Right.
Okay, good. So the missing cause of gravity is the next question that we want to address. And Newton, of course, claimed not to address the question of cause. He's only developing a mathematics. His maxim, of course, you know, his writings were in Latin, which was the language of science of the day. Hypothesis non bingo, I make no hypotheses. I only express mathematical relationships. A mathematical description of gravity, not the cause. He recognized, as many of you know, an instantaneous relationship between, I mean, there's no time dependence in his famous formulas, and yet he was troubled by that, but he didn't claim it to have a cause. He only had a mathematical description, and it worked. It still does. Let's go on. Okay, so what Steven Rado was claiming in his paper is not merely the mathematics, but the cause itself. Why does gravity operate the way it does? And his strategy is threefold. Number one, to reinstate an ideal gas cosmic ether, and I have to be careful here, make sure I describe what I hopefully get this right. By gas, he means particulate. In other words, there are particles within this ether. It's not fluid in the sense of being continuous. Is that right?
Fluid is particles too.
Okay. Okay. All right. Okay. It's not continuous, it's particulate. Is that correct?
Right.
Cosmic, existing everywhere, and ether in the sense of something similar to Faraday's energy surrounding space. Okay. He's going to then apply that to Newtonian fluid dynamics, and then he's going to he's going to apply fluid dynamics to the original Descartes solar vortex theory. So he's kind of going to go back a couple of pages and use the mathematics of Newton with Descartes' ideas. Interesting idea. And it's ironic because Newton was quite critical of Descartes. So it's an interesting mix. But let's go on and see what we get out of this. Okay, so the step one in the process is to refute, first of all, Newton's attack of Cartesian vortex. And I'll have to confess, I'm not sure if I'm going to get this right because I didn't quite understand it myself, but I'll do the best I can. Kepler's third law is now P is period, which you could replace that with a T. As we know, that the period or the time squared is over the radius cubed is a constant. That's, in other words,
it's an empirical result.
It's an empirical result.
Based on observation.
Right. And Newton then noticed his argument. Now you're going to have to help me here because he's arguing that the radius, the radius per time, which is a velocity, is proportional to 1 over r squared, being the force, 1 over r squared force in his famous equation. Is that? I didn't quite understand that section, so I apologize for not. That's what you wrote, and I didn't quite follow it. I'll have to.
What Newton did is took Descartes' vortex, throw away the cause part of it, the natural vorticity which creates rotation, and for the cause, he said that it's the mass attribute. Mass itself has this attribute that attracts other matter. All matter attracts other matter. Okay. And based on that, he re-derived Kepler's basic empirical equation based on his gravitational force.
Okay. Okay, but as I understood, what I was looking for in the book, and I couldn't honestly, wasn't able to peek out, was I was trying to see what Descartes' argument was and how Newton refuted it, and I honestly couldn't see that in what was there. But
Descartes didn't have an idea other than there is a vortex and carry around.
So he didn't have any math, he didn't have any formulas or anything. It was just
but he had a mechanical solution,
okay,
but nothing scientific or mathematic.
Okay. Well, the electrokinematics also derives Kepler's third law, but he uses it with the Descartes vortex. So that's the difference, a different approach to get the same thing. So let's go ahead.
Including the sync vortex idea, which gives the force, the central force.
Okay. As I understand it, if you look at these pictures, what we're looking at is 3 components or of a similar, of a sync vortex, or 3 different types of fields. So I had a question about this myself. I was wondering if the radial component and the rotational component, when you add them together, you can get the third, so it's kind of a linear combination.
That's the sync vortex.
Yeah, okay. So they're not 3 independent components, they're 3 there's two independent components and
working
one
together.
working together. Okay. So in the book, go ahead, the next slide. In the book, go ahead. He identifies the three components. One, radial, which is the direction of centripetal forces or acceleration, the tangential or the orbital, and the vortical, which I would say is the sum of the two. So I asked that question because it wasn't clear in the book. Number three is the vectoral sum of the two, and I suppose depending on the weight of the two, you get different vorticities. Okay.